Welcome back, everyone, to MAE170. This is lecture 12 in week number 7. I'm starting with the notes from lecture 11, and I kept the notes together because it makes more sense to have both lead compensators and lag compensators together because it's one topic. Then we will have another set of notes for the PID controllers. All right, so last time we saw the phase lead compensators and their design in the root locus context. And today we are ready to see the other face of the medal, that is the phase lag compensators. As I said last time, while the lead compensators are used in order to meet the main requirements in terms of settling time, percent overshoot, rise time, etc., that is, we use the lead compensators in order to bend the root locus of the uncompensated system so that it passes through the dominant poles that we are seeking. The lag compensators are instead used in order to decrease the steady state error. That is the function that they have when the design is done in the root locus context. We also saw last time that it really makes sense to use lag compensators in order to decrease the steady state error when such error is finite. If the error is infinite, there's no lag compensators that you can add that will reduce the error. And if the steady state error is already 0, well, obviously you cannot decrease it any further. So we're really looking at systems that have a finite steady state error. So that happens, as we saw, in 3 combinations. We can either consider type 0 associated with the step input, a type 1 with the ramp input, or a type 2 system with the acceleration input. So all these 3 combinations will produce a finite steady state error. So now we're going to see how to design a lag compensator using an example. And then, as we did last time, we will have a summary at the end with all the steps needed for the design. All right, so we'll consider a plant with the following transfer function. G of s equals 1 over s times s plus 2. So the open loop, let's analyze briefly this plant transfer function. We have a type 1 system because we have one pole at the origin, and this system is a second order system because we have 2 poles, one, as I said, at the origin and the other one at -2. Now we have 2 goals. We want a velocity constant equals to 20. So this is equivalent of saying we want a steady state error that is less than a certain value. Remember that when we studied the system type numbers, we talked about the position constant, the velocity constant, and the acceleration constant. So they're usually utilized instead of or in place of a requirement directly on the steady state error. So instead of saying, for instance, that the steady state error should be less than 0.1, you could say the velocity constant should be greater than a certain value. So in this case, we want exactly a velocity constant of 20. Here in the original problem, the input is not given, the nature of the input. However, since we're dealing with the type 1 system, we can go back to our couplings here, and we see that we really must deal with the ramp type of input. Because again, type 1 system has to be matched with the ramp input in order to create a finite steady state error. So the input is a ramp input, and in the S domain, we know that this is equal to 1 over s squared. Finally, the other requirement that we have is that the damping ratio for the dominant poles should be equal to 0.447. All right, so we want one, the velocity constant equal to 20, and two, the damping ratio associated with the dominant poles to be equal to 0.447. As we did last time, the first thing that you want to check is whether or not the uncompensated system meets the requirements, because if that is the case, there's no need to introduce a compensator. So let's go ahead and let's check if the requirements are met without the compensator. So let's analyze the uncompensated system. So we have that our input is the ramp input, that is 1 over s squared. Then, well, as usual, let a constant gain that can be varied. And finally, we have the plant as 1 over s times s plus 2. Very well, let's check the error. And from the error, we can find the velocity constant. So the error, as usual, it is r of s times 1 over 1 plus k times g of s. So in this case, we have 1 over s squared times 1 over 1 plus k over s times s plus 2. And so this is s times s plus 2 over s squared times s plus 2 plus k. This s cancels with the square. And now, always in assuming that the final value theorem is applicable, we can find the steady state error, that is the final value for the function e of s. So in the s domain, that is equal to the limit of s that goes to 0, or for s that goes to 0 of s times e of s. And so we have s times s plus 2 over s times s plus 2 plus k. Now we have this s goes away with that. And so we're left with 2 over k. Now, if you go back to the lecture in which we discussed about the system type numbers, you saw that the steady state error for type 1 systems coupled with ramp inputs is also equal to 1 over kv, where kv is our velocity constant. So it means that the velocity constant is equal to k over 2. So in other words, since we're looking at kv equals 20, we must find k that is equal to 40. But that might not be the case because we also have the other requirement in terms of the dominant poles. So let's take a look at the dominant poles for this closed loop transfer function. We're given that the damping ratio is 0.447. But what about the natural frequency associated with them? Well, we can infer that by drawing the uncompensated root locus. So the uncompensated root locus, we start with the characteristic equation, which is 1 plus k times 1 over s times s plus 2 equals 0. It's already in the canonical form. We can place the open loop poles. We don't have any open loop zeros, so the open loop poles are at -2 and at 0. And you know very well by now that when we have only a couple of real poles, the root locus looks like this. So you connect the two poles And then right in the middle, there's going to be a breakaway point. So the breakaway point is going to be a -1, and then the two branches will depart perpendicularly to the real axis, maintaining the value at -1. So you see that if the damping ratio is less than 1, it means that the dominant poles must be on the complex part of the plane. So we have to be off the real axis. So we must be somewhere on these two branches. So in other words, we know that the real part of the dominant poles has to be equal to -1. Or we can write that minus zeta omega n has to be equal to -1. Why this? Because once again, minus zeta times omega n is the real part of the dominant poles. And in fact, we have the usual way of writing them. By now we should know this. And why do we write them in the complex conjugate format? Well, that's because the damping ratio is less than 1. So as I said, we have to have complex conjugate poles. All right, so given the fact that minus zeta omega n has to be equal to -1, this implies that omega n has to be equal to 1 over zeta. We have the value of zeta, which is 0.447. So omega n is equal to 2.237 radians per second. Don't forget the unit. Now we have both the natural frequency and the damping ratio for these two poles, so we can actually find the precise location of them. So we have -1 plus or minus I. Now omega n is 2.237 times square root of 1 minus 0.447 squared. And so if you go ahead and perform the calculations, you'll see that we have a nice integer for both the real part and the imaginary part, having -1 plus or minus I2. So we can actually locate the dominant poles now on the complex plane. There you go. 1 and 2. So we can call it as dominant poles 1 and as dominant pole 2. So these are -1 plus 2i and -1 minus 2i. All right. Now, in order for the uncompensated system to meet the requirements, we said that the value of k has to be equal to 40. So if that is the case, in other words, if we land on the dominant poles for k equals 40, then we meet both requirements and we're golden. However, this is going to be a coincidence if it happens. Most likely it won't happen. So let's see the actual value of k at which we land on the dominant poles. So how to do that? Well, we have to solve the characteristic equation. At the value of one of the two dominant poles. Once again, I'm going to use the one with the positive imaginary part, that is -1 plus I2. And the only unknown that we have is the value of k. So I can simply use the magnitude equation. So I can find the magnitude of k times 1 over s times s plus 2. has to be equal to the magnitude of -1, which is 1. But this has to be evaluated at s equals -1 plus I2. Therefore, we have that the magnitude of k times 1 over, now we substitute -1 plus I2 for s. So we have -1 plus I2 times -1 plus I2 plus 2. And this has to be equal to 1. So going ahead with the calculations, we have 1 over square root of real part squared, 1 plus imaginary part squared, that is 4, times square root of real part squared. So -1 plus 2 is 1. So 1 once again, plus imaginary part squared, which is again 4. So this has to be equal to 1. In other words, k happens to be equal to 5. And this is not the 40 that we were expecting. So for the uncompensated system, the velocity constant, since that was equal to k over 2, is 5 over 2, which is 2.5, which is definitely less than 20. So for the dominant poles that we are requested to have, we are not meeting the requirement in terms of velocity constant. Therefore, we do need a phase lag compensator. As usual, we choose a compensator in the form of S plus sigma Z over S plus sigma P. Now, since we want a lag compensator, we know that the ratio between sigma P and sigma Z, that is what we called alpha, must be less than 1. So in our block diagram, obviously, the compensator is going to be placed over here. All right, with the output, and our input is always 1 over s squared. Okay, so now we are ready to compute the steady state error for the compensated system. So we always have limit for s that goes to 0, s times e of s, but what is e of s in this case? It is r of s, which is 1 over s squared, times 1 over 1 plus k s plus sigma z over s plus sigma p times 1 over s times s plus 2. That is gc and g. Okay, let's compute this limit. And I invite you to redo the calculations because it's going to be very useful, as you saw during the exams. I saw that many of you lost points because of wrong calculations. And so, the more exercises you do, the better, and the faster you'll become at performing such calculations. All right, so here we have, once again, 2 over k, but now this, which was the uncompensated steady state error, is multiplied by sigma p over sigma z. And that is, we have 2 alpha over k. Now this has to be equal to 1 over kv. Obviously, now it's compensated. So the velocity constant is equal to k k over 2 alpha. The k over 2 alpha was the velocity constant for the uncompensated system. So we have that kv for the compensated is equal to kv for the uncompensated divided by alpha. And therefore, we have that 20 has to be equal to 5 halves times 1 over alpha. And this allows us to calculate the value for alpha, which is 1 over 8. 1 over 8 is 0.125, which is less than 1, and therefore this checks the fact that we're dealing with the lag compensator. Remember, alpha has to be less than 1 for us to have a lag compensator. If it had been greater than 1, we would have had a lead compensator, and that was not really our goal. So if you find a value of alpha greater than 1, check your calculations. Okay, so now we have alpha, that is, we have the ratio between the pole and the zero of the compensator. But we don't really know where the pole and the zero are. For instance, we could have the pole at minus 1, and then the zero at minus 8. This would work technically, because minus 1 over minus 8 is 1/8, which is alpha. But with using the same reasoning, we could have the pole at minus 1/2 and the zero at 4. Minus 0.5 over minus 4 is still 1 over 8, which is still our alpha. So you see there are an infinite amount of choices for the poles and for the pole and for the zero of the lag compensator. So now we have to make an arbitrary choice. If you remember what I said last time, when we're dealing with lag compensators, we want both the zero and the pole to be quite close to the imaginary axis. And that is because if we do so, the overall angle that we are introducing with the lag compensator is going to be very, very small. You can think about this in terms of when you have a small angle associated with a compensator, you're not going to modify the root locus much. The larger the angle associated with the compensator, the more the uncompensated root locus will bend. The objective for a lag compensator is not to modify the root locus, it's just to modify the steady state error. So we don't want the pole and the zero to be far apart. And therefore, we must choose both of them to be quite close to the imaginary axis. So how do we determine what is a good choice? Well, once again, here we have this rule of thumb that tells us to pick sigma z as the real part of our dominant poles divided by 50. Again, this is a rule of thumb. It could be divided by 60, 70, 40. You don't have to pick exactly 50. This is usually done though. All right, so in this case, zeta times omega n was equal to 1. So we have 1 over 50, that is 0.02. And so we have automatically the position of the zero. The zero is going to be at minus 0.02. So once we have the zero, the pole location follows suit, because sigma p is equal to alpha times sigma z. We have both alpha and sigma z. And so we have 1/8 times 0.02. And so we find the value for sigma b and therefore the location of the pole. And in this case, it is equal to 0.0025. So you see that both the zero and the pole are quite small in magnitude. That is, they're very close to the imaginary axis, and that's exactly what we want. What we care of is really the ratio between the two, because the ratio between the two, alpha, will determine the factor of decrease of the steady state error. But we don't want to modify the root locus. We don't want the root locus not to pass through the dominant poles anymore. All right, so with this choice, we can write the transfer function for the compensator. So it's going to be s plus 0.02 over s plus 0.0025. Now we can check that the overall angle associated with the lag compensator is indeed small. And remember that I told you that usually that is less than 2 degrees, calculated at the dominant pole. So let's actually do so. If we substitute s equals -1 plus 2i, which was one of the locations of the dominant pole, we have that the transfer function of the lag compensator is -1 plus 2i plus 0.02 over -1 plus 2i plus 0.0025. And so the angle is going to be arctangent of 2 over -0.98 minus arctangent of 2 over -0.9975. If you calculate these two angles, this is going to be 116.1 degrees minus 116.5, which is -0.4. So the introduction of this lag compensator will determine a lag of 0.4 degrees. 0.4 is clearly less than 2, so it's a good lag compensator. Now, if we draw the root locus for the compensated system, we'll see that, well, let's write the characteristic equation. All right, so we have 3 poles, the 2 original uncompensated poles at 0 and at -2. Then we have the extra pole introduced by the compensator itself at -0.0025. And then we have a 0 at -0.2. Here we go. Remember that earlier, the uncompensated root locus looked like this. All right. Now, since we've introduced a compensator, the root locus must change. This is inevitable. It cannot remain the same. So we are expecting the root locus not to pass exactly through the dominant poles. However, as I said, if both the pole and the 0 of the compensator are close enough to the imaginary axis, that is, if the angle introduced by the compensator is quite small, the deflection that the root locus will take is really minimal. And you can in fact, plot the root locus of the compensated system, and it's going to look like this. So now these are the segments of the real axis that belong to the root locus. The segment between the 0 and the pole of the compensator is not part of the root locus anymore. So we must have a breakaway point between the two poles and then a break-in point right before the 0. And so it's slightly the main branches that depart from the real axis. Well, they depart at there's going to be a breakaway point slightly to the right of -1. So it's not exactly at -1, but then the two branches will be very close to the uncompensated ones. So pretty much the new compensated root locus will still pass through the dominant pole. So very, very close. So overall, the root locus hasn't changed much. Moreover, if you actually plot it in MATLAB, you'll see that this circle here of the new root locus, it's very, very, very tiny. So this is what I drew is not to scale. You almost cannot see it because of how tiny it is. In fact, both the compensated 0 and pole are very, very close to the imaginary axis. So if you really, I invite you to do so. Plot the root locus for the compensated system, and you'll almost see that it looks identical to the uncompensated one. But once you zoom in, then you're gonna notice this structure here with an extra breakaway point and the extra break-in point to the right and to the left of the pole and the 0 of the compensator, respectively. All right, so we've finished with the design of the lag compensator. As you see, it's quite easy once you have the ratio between the pole and the 0. That is, once you have alpha, you choose arbitrarily the point, the placement for the 0, and then the placement for the pole falls is determined by alpha itself. Okay, so let's review the design steps for the lag compensator in the root locus context. The first thing that you want to do is to draw or obtain the root locus for the uncompensated system and determine the transient performance specifications for the system and locate suitable locations for the dominant poles that satisfy the specifications. You might have, like in Tuesday's lecture case, you might have a chance to choose your dominant poles. In this example, you couldn't really choose the dominant poles. The location of such poles were forced, already given. Now, if you see that your system, your uncompensated system, does not pass through the dominant poles, then you would want to design a lead compensator first. But we've already seen that. But that's always step number one. If your uncompensated system does not pass through the dominant poles locations, then design a lead compensator first. Then you want to compute the gain K at the dominant pole location and determine the steady state error, or equivalently, the error constants, either position constant, velocity constant, or acceleration constant. So in other words, you want to find the steady state error for the uncompensated system or for the system with the lead compensator, but I'm going to call it uncompensated because it doesn't have the lag compensator yet. Now you compare your uncompensated steady state error with the desired one, the desired meaning the one that is required. And if your steady state error is greater than the desired one, then you can determine alpha necessary for the compensator. Then we have the arbitrary step of placing the 0, and you take it as 50 times smaller than the real part of the dominant poles. And then the placement of the pole of the compensator is just sigma z times alpha. And then as the last step, you want to check the overall angle introduced by the lag compensator. You want to check that is less than about 2 degrees. And if that is not the case, then you have to repeat steps 5 and 6. That is, you have to choose another location for sigma z. Let's say that you find an angle that is too large, let's say 10 degrees, then you want to choose a value for sigma z that is smaller. So instead of using 50 here, you might want to use 100 or something like that. All right, so now a brief summary of both the lead compensator and the lag compensator design using the root locus. So we have that for both lead and lag compensator, their transfer function is s plus sigma z over s plus sigma p. In other words, we're introducing one real 0 and one real pole. We've defined alpha as the ratio between sigma p and sigma s, but for a phase lead compensator, this value is greater than 1. That is, the 0 is to the right of the pole, and usually these two are quite far away. Whereas for the phase lag compensator, the ratio alpha is less than 1. That means that the 0 is to the left of the pole, and both 0 and left are quite close to the imaginary axis. And that is because the objective for the lead compensator is to bend the root locus to the left in order for it to pass through the location of the dominant poles that you want. Whereas the objective of the lag compensator is to decrease the steady state error. Now, we have something that we can achieve that I call the objective, but both the lead and the lag compensators will have a side effect. So the side effect of the lead compensator is that the steady state error will increase, but of course, that can be corrected by using a lag compensator later on. And the side effect of the lag compensator instead is that it bends the root locus to the right. So it moves it away from the dominant poles. However, if the angle associated with it is less than 2 degrees, it doesn't move that much, as we saw in the example. So the side effects are really not a big deal, because the side effect of the lead compensator increasing the steady state error can be corrected using a lag compensator. And the side effect of the lag compensator of bending the root locus to the right can be minimized by using a compensator that has both 0 and pole close to the imaginary axis. All right, so this is all for the compensators using the root locus methodology. We're going to see the same compensators later on and their design using the body plot. So this is all for this part. And the next part will be PID controllers. So I'll see you there.